Okay, so shall we proceed here to the stereochemistry for E2? Okay. So now, what type of stereochemistry can we have for an E2 reaction? Remember, an E2 reaction forms a double bond. So is it going to be forming stereocenters? It can't be forming stereocenters because a stereocenter has to be attached to 4 different things, and something that's double bonded is only attached to 3 things. So at first you might think there isn't any stereochemistry, but you would be wrong. There is some stereochemistry. It's a different type of stereochemistry though than RNS. It's not RNS stereochemistry. Let me ask you this. Alright, so if you look at these 2 molecules, they look pretty much the same. They're both butane. They're both 4 carbon chains. 1, 2, 3, 4. They're both butane. The difference is here, the 2 methyls on the ends, here the 2 methyls are both pointing up. And here 1 methyl is pointing up and 1 methyl is pointing down. But would we consider these to be the same molecule or 2 different molecules?
Same.
We'd consider them to be the same, even though the pictures look different. Why do we consider them to be the same? Well, things are the same if you can rotate or flip them so that they superimpose. 2 pictures are the same if you can rotate or flip them so that they superimpose. Well, is there some way we could rotate this methyl group so that it would be up here and superpose on here? Well, that would involve rotating around this single bond. Can you rotate around a single bond? Yes. So we could just rotate this methyl group to be in this up position over here, rotating around this single bond. That means even though these pictures look different, we would really consider these identical molecules. All right, so these are identical molecules. Now let's consider these 2. This is butene. Butene, it's still got 4 carbons, but it's got a double bond. Now again, we've got 2 methyls on the end. Here, 1 methyl is pointing up and 1 methyl is pointing down, and in the bottom picture, both methyls are pointing up. So again, the 2 pictures look different. But we know that even if the pictures look different, they may or may not be different molecules.
They're not the same because you can't rotate around double bonds.
That's right. We can't rotate around double bonds. Looks like you guys are familiar with that. So we would consider these to be 2 different molecules. These are 2 different molecules. There's no easy way to rotate this methyl from below to above because that would be rotating around a double bond. There's no free rotation around a double bond. So the upshot of that is there was no interesting stereochemistry for these 2 pictures. The stereochemistry was not interesting because it doesn't matter whether you draw the methyl pointing up or down. It's really the same molecule either way. But there is interesting stereochemistry here because it does matter where you put the methyl. Stereochemistry just means the arrangement of the atoms in space. Well, here the arrangement of the atoms in space doesn't matter because you can just rotate to get a different arrangement. But here, the way you draw the arrangement in space does matter because there's no free rotation once you choose one of those orientations. So there is stereochemistry here, even without stereocenters. This is a new type of stereochemistry. Because there's no stereochemistry here, we don't need different names for these 2 molecules. Actually, I guess there is a way to name these conformationally. But for the most part, we wouldn't need to give these different names. But these are separate molecules, so they do have different names. Do you guys know what the different names are for these 2 types of double bond?
Is it like the sin, or is it like the... Oh, the sin and the anti?
So this would be cis and trans. Cis and trans. Syn and anti is actually a related idea, but the conventional name for this would be cis and trans. Which of these is trans? Yeah, maybe you guys are familiar with the idea that trans is a prefix that means across, like transatlantic means crossing the Atlantic. Well, these are across from each other, basically. Or transatlantic means going to different sides of the Atlantic. Well, these are on different sides of the double bond. One's on top, one's below. Cis then means same side. So cis means same side here. So this is cis and this is trans. So just like we've learned R and S naming for one type of stereochemistry at a stereocenter, we also have to learn cis and trans naming for a different type of stereochemistry around a double bond. So here's the stereochemistry around double bonds, cis or trans. So that's what you have to worry about. So this is what you have to worry about for an E2. An E2 doesn't produce a stereocenter, but an E2 does produce a double bond. So you have to ask, am I going to produce the cis double bond or the trans double bond? That's the stereochemistry.
How do you know?
It's a whole big thing, so I'll have to go through it step by step. Okay, so that's the question. How do we decide whether it's going to be cis or trans? Now, first of all, sometimes it doesn't make any difference. After all, take a look at the product that we made here. Well, since all four substituents are the same, there is no cis or trans distinction over here. So a lot of the time you'll produce a double bond where there is no difference between cis and trans. Then you don't need to worry about it. So in many cases you won't need to worry about it. You really only need to worry about it if there's a substituent on both of these two carbons over here. Because unless there's a substituent on the left and a substituent on the right, they can't, you need one substituent on the left and one substituent on the right, so they can either be on the same side or different sides. So we need at least one substituent on each of these carbons. Okay. All right, so cis and trans did not come up here. I wanted to start with a simple case, but now we can do a more complicated case to see where we get the cis and the trans. So I'll erase this and have this in your notes. Okay. Okay. All right, so let's see. What type of mechanism are we going to have here? How do we know?
We have a big bulky base.
Yeah.
And stereochemistry.
So there's, yeah, as long as you have a big bulky base like this, it almost has to be an E2 reaction. That's right. By the way, the name for this is chert butyl oxide. This is such a popular bulky base that you should know that name. I actually used that name on the handout at the bottom of page 3 for bulky bases. Chert butyl oxide, that's the O with the negative over here. Okay. You can see why it's called butyl because it has 4 carbons. 1, 2, 3, 4 over here. And it's called tert because this is a tertiary carbon. It's tertiary because it's attached to 3 other carbons over here. Okay, so that's tert butyl oxide. Okay, so this is going to be E2. All right, now let's see here. So we can go ahead. Let's see what's the best way to explain this. Okay. Now, it turns out that the best way for a beginning student to handle this is to use a Newman projection. So we're going to use a Newman projection here. So let's say that somebody was looking at the molecule from this direction. Let's see if we remember how to draw the Newman projection for this. So take your time and let's see if we can do that.